How do you even begin to draw something you can't see? I mean, think about it. Forces like electricity are everywhere, shaping our world, but they're totally invisible. So how on earth are we supposed to visualize an electric field? All right, so here's our game plan for this explainer. We're going to start with why we even need to visualize these forces. Then we'll look at the simplest possible case, just one little charge. After that, we'll get into the really clever part, how these drawings show strength. We'll cover the non-negotiable rules for drawing them, map out some more complex fields, and then we'll wrap it all up with the key takeaways.
You know, the real challenge here is that an electric field exists at every single point in space around a charge. If you tried to draw an arrow for the force at every point, well, your page would just turn into a big black smudge. We need a smarter, more elegant way to do this.
And that is the central puzzle. It's a question that brilliant minds like Michael Faraday wrestled with. He knew these fields of force were real, but he needed a way to see them in his mind's eye, to make them intuitive.
And this was his absolutely genius solution, the electric field line. It's such a simple but powerful idea. Just think of it like a current in a river. If you pick any spot on one of these lines, the direction the force is pushing right there, it's just the tangent to the curve at that exact point.
So let's see how this actually works. To really get a feel for field lines, we've got to start with the most basic thing there is, a single lonely point charge.
And there it is. For a positive charge, it's pretty straightforward. The field lines just shoot straight out in every direction. The way to think about this is to imagine you have a tiny, imaginary, positive test charge. It's just a little probe we use in our heads to map things out. If you place that little guy anywhere near the big charge, the arrow on the line shows you exactly which way it's going to get shoved. Straight away.
Okay, so we've got the direction down. The arrows tell us which way the force is pointing. But hang on, we all know the electric force gets weaker the farther away you get. How can a simple drawing show that? Well, this is where the true genius of this whole idea comes in, because the strength is baked right into the picture too.
This is where the visualization just becomes so powerful. The strength of the field isn't about how long the lines are or anything like that. Nope, it's all about how crowded they are. This image shows it perfectly. Just look at those two little square areas. They're the same size, but the one closer to the charge at P1 has a bunch of lines poking through it. The lines are all bunched up. Now look at the one farther away at P2. The lines are spread out and way fewer of them pass through. The rule couldn't be simpler. Where the lines are dense, the field is strong. Where they're spread out, the field is weak.
And this just nails the concept. Up close, on the left, the lines are packed shoulder to shoulder. That's a strong field. But as you move away to the right, those exact same lines have to cover more and more space, so they naturally spread apart. Their density drops, and that's our visual signal that the field is getting weaker. It's an incredibly intuitive way to see how the field's strength changes.
Okay, let's get just a little technical for a second, but stick with me. This whole relationship works because of a geometric idea called a solid angle. The easiest way to picture it is like the cone of light from a flashlight. The number of field lines inside that cone stays the same no matter how far away from the charge you get.
But the area that cone covers gets bigger and bigger as you move away. In fact, it grows as the radius squared, or r squared. So if the number of lines is constant, but the area they're spread over is growing like r squared, then their density has to drop as 1 over r squared. And that right there is the famous inverse square law. It means if you double your distance, the strength drops to a quarter. Triple the distance, it drops to a ninth. It's a fundamental rule of the universe.
So you can't just draw these lines however you feel like. To make sure they actually represent reality, there are a few very strict fundamental rules we always have to follow.
And here they are. First, lines always start on positive charges and end on negative charges. Second, they're continuous. A field doesn't just vanish and reappear somewhere else. Third, and this one is a big one, two field lines can never ever cross. And fourth, for static charges, these lines never loop back and bite their own tail.
Okay, let's hit pause on that third rule, because it's probably the most important one on the list. Why is it so impossible for two of these lines to intersect? What would even happen?
Well, think about it. If they crossed, at that one single point where they meet, the field would have to be pointing in two different directions at the exact same time. And that's just nonsense. A force can only point in one unique direction at any single location. It's physically impossible. So the field has to be unique at every point in space, which means the lines can never cross, period.
All right, now that we have our rule book, let's put it all together and see how these simple rules can create some truly beautiful and informative maps for more complicated situations. So, on the left, there's our old friend, the positive charge, with lines shooting outwards showing repulsion. But on the right, we have its counterpart, a negative charge. And here, you can see the lines all point radially inward, showing attraction. This follows rule number 1 perfectly. Lines start on positive, and they end on negative.
And this is what happens when you put them together. How cool is that? This elegant pattern is called an electric dipole. And it's not just a pretty picture, it's a perfect map of the forces at play. Look at how every single rule we just learned is being followed. The lines start on the positive, they swoop over and end on the negative. They never cross each other, and they flow smoothly, perfectly mapping out the path of attraction between them.
Whew, okay, we've covered a lot of ground here, from the basic idea to the hardcore rules and patterns. Let's just boil it all down and summarize the most important points.
The bottom line is this: electric field lines are an incredibly powerful way to see the invisible. Just remember, how close they are tells you the strength. That strength drops off with the square of the distance. They always point away from positive and toward negative. They can never ever cross, and for static electricity, they don't form closed loops.
And you know, that last rule leaves us with a really fascinating question to chew on. We've just established that these electrostatic field lines have clear beginnings and endings on charges. So, what kind of field out there does create lines that are continuous closed loops? What kind of force has no beginning and no end? It's something to think about.